Hello everyone, welcome to Wibbily, Wobbly, Timey, Camly. My name is Delon, or Darren. This is a project done in collaboration with Gabriel Redan. Time processing is messy. Sometimes we get intervals which cross the day boundary, in which case we do not have the same date for the starting time and ending time. Sometimes the interval does not have a fixed duration due to things like daylight saving time. And for recurring intervals, we may not be able to compute them easily depending on the time zone, again, due to a varying time zone offset. And perhaps more critically, who remembers the time zone offset of a particular day anyway? Introducing Timey and Friends. It's a scheduling toolbox written in OCaml. It resembles a domain-specific language, or DSL. It provides accurate daytime handling with time zone via the time description component. It provides some natural language processing support via the parsing component. Overall, it is highly expressive and flexible. Here we provide a small example to figure out the common time Gabriel and I have for the conference question time. So we can specify a time constraint as free time, relying on Timey parse to parse our natural language string in English. We specify the conference time. We specify our own time zones, and we finally combine the time constraint. And we finally, and then at the last line, we attach the individual time zones to the time constraint, and we get our final scheduling object or constraint. And the result is a lazy sequence of pairs of timestamps. We start off by introducing the individual API components. So the first one, as we've seen in the example, is the Timey parse component. So it translates a string into a Timey object, which is the scheduling object. So here we have two examples, and we use the as expression serialization to represent the Timey object itself. And we can see it's equivalent to the direct construction, but it's often quicker to just ask Timey parse to construct simple things like these for you. So now we move on to direct construction of simple terms or atoms. So they ingest concrete information. So in here they would ingest a particular timestamp, for instance. And we can express simple things like the time from now, or the time before a particular timestamp. Next, we move on to something more powerful, and these are very close to how we specify time naturally. Namely, we tend to specify a set of date and time with a certain pattern. So you would say something like the year 2021. Month of June, some weekday to some other weekday, and so on. The nicety of this is that we don't have to care about the actual timestamps or the actual or the particular time zone specific information, and we leave that to Timey to resolve. In terms of intervals, we can specify explicit intervals, which are just pairs of start and ending timestamps. We can also specify intervals that follow some pattern for the starting and ending time, but they don't fall on the hour boundary or some other boundary that allows a efficient specification via a single pattern. So for instance, 5:33 p.m. to 6:15 p.m. We can't specify it by picking just a single hour. So in this case, we could use a pattern matching interval. So we can either do a direct construction, or we can do the equivalent via asking for Timey parse help. Next, we begin to talk about combinators. So we start off with intersection. So this is the same idea as a set intersection. So we pick out the common intervals between two expressions. So in our first example, we specify the time from now till the end of the domain, so end of year 9999. And we also and then we intersect that with the time before a particular date time in Paris. And combining the two, we have specified a range. And the next example we have, we pick out all the Thursdays, and we also pick out all the Septembers. And by intersecting, we are asking Timey to pick out all Thursdays in all the Septembers. Then we have union, so it just merged the intervals derivable from the two expressions. So here it's like all Fridays or the 29th of any month. We also have not, which is complement, so it flips a particular expression. So in this case, we have not Friday. So this is equivalent to picking out all the weekdays which are not Friday. And combined with intersection, this overall reads all 20th, which are not Fridays. Next, we have an important one. So this is with time zone. This allows us to attach a time zone to a term. So the nicety of this is that this allows us to reuse the same term across multiple time zones. And we can also mix and match terms with different time zones together using other combinators. And finally, we have trunking. So this is very similar to the lazy sequence selectors you would see in other libraries. So we specify a trunking method, in this case, disjoint intervals. So it just means that the selector will receive a lazy sequence of disjoint intervals. And then we specify our selector. So it takes every other, so take nth means take every nth. So we take every other item or interval and then pass it on to taking the first 20. And we specify a pattern, picking out all the Mondays from now. So overall, this reads, take every other Monday starting from now, and then pick out the first 20 only. So having a powerful API is nice, but it's not very useful if it ends up being very slow to use in practice. So to tackle this, we address the efficiency concern in three main ways. So the first one is about the memory usage. Internally, everything is a lazy sequence. This gives a better memory footprint compared to other data structures that demand the intervals to be provided up front. So this would include, or at least a naive use of interval trees. The second way is to speed up a commonly used primitive. So in this case, pattern matching primitive is very commonly used by the other constructors and other logical components. And speeding it up would help a lot because essentially it is a hotspot. So we begin by explaining how pattern matching works. So pattern matching is essentially finding out what what date times inhabit a particular pattern. So it's somewhat like a regular expression in some sense. So to achieve this, we use a depth-first search. So in this case, the root of our search tree is a year, and followed by the month, and followed by the day, and so on. The short circuiting refers to the observation that if after a level, so in this case after the day, all the remaining levels are wildcard. So in other words, no constraint. So it could be any hour, any minute, any second, any nanosecond. then we can actually stop at the last concrete level. So we can actually stop after processing day. So in this particular case, we can actually pick out the first interval, namely the start of 20th and the end of 20th. So the benefit of short-circuiting is that we no longer have to spend unneeded computational time to go through all the hours, minutes, seconds, nanoseconds, just to combine back into a contiguous interval. Next, we have search space optimization. So this comes from the intuition that when we have a chain of intersection, the term with the smallest search range gives us the biggest clue as to where to begin and where to end. In this case, since one of the we notice that one of the term has a search range of 2021. And so we can naturally conclude it's pointless to go through any other year. And so we can propagate this search range or bound to the neighbors across the chain. And next, we have dynamic search space optimization. So this works for union. So this comes from the observation that if we have a very large interval, then it's not useful to go through all the small intervals that would be within the large interval anyway. So as a concrete example, we have here one that matches the year 2021. The one matches all the 5 to 6 p.m. of year 2021 to 2023. So intuitively, it's pointless to actually go through all the 5 p.m.s in 2021 because we are including the entirety of 2021 in our result anyway. So there's not much point in going through the list of all the 5 to 6 p.m.s in 2021 only to add it into the larger set and not introducing any effect essentially. So to mimic that intuition, what we have is that if we can visualize this as a message sequence chart. So if the union operator spots a large interval, so an interval that's greater than 30 days, let's say, then it will propagate the search space, or more precisely, it will slice the search space equivalent to asking the other terms to skip to a particular time point. And so this avoids the needless search that does not introduce a observable effect. So in this case, we just ask the other term to skip to 2022 instead and start returning the results from then. Finally, some remarks on testing. So we use some unit tests for very basic checks. We use property-based testing for a lot of the logic components. And then we use fuzzing when we still want property-based testing, but randomized input is too slow. So we want something that can time out and something that can make a educated guess during the search. And so a crowbar and AFL is a good fit for this. We use this to test the more time-consuming logic components. And we also use this to test the overall implementation by comparing it to a simple one. So a simple one has a much lower code complexity as it relies on interval trees as implementation. To conclude, we presented 3 components: time desk, Timey, Timey pass. They together form a toolbox that is expressive and flexible. Namely, they provide first-class support of time zones, and the combinators constructors work robustly across time zones and boundaries, as they are based on pattern matching. They are efficient, namely they resolve quickly in the usual cases, and they have a low memory footprint. And lastly, the toolbox is quite smart. Namely, one can construct common terms quite easily via Timey pass. Thank you.